Okay. So last time we left off on this was at integration, and I want to make sure that everybody understands that this right here is the area under a curve, okay? Now I know that these curves look like lines right now, but they're not. They're actually do have width, and they have an area under that curve, okay? And so if you've taken calculus, then you may have heard of integrations. Has anybody heard of integrations before? Yeah. Most of you probably have taken a calculus of some sort at this point. And so this is literally integration as in calculus. It's not done the same way a calculus program would, like you've been taught in calculus. It would be done with matrices usually, because it's a computer. Which actually, funny enough, many of you have done in the biostats. Done a little bit of matrix. Okay, I know, you may not remember it. It's okay. Okay, fair enough. I feel like most of your trigger words are either me or Phillips. uh, okay. And so when you look at these, what you want to do is, first off, remember it's not the height. And we're going to be talking about something in just a little bit, the next slide, in fact, that's called splitting. Okay? And so what happens in there is the height from a signal actually is going to come off onto these other parts where it's going to be different states that the hydrogen can be in. Okay? And they're going to be modified just a tiny, tiny little bit. Right? It's kind of like when you're trying to represent where you are on your desk, right? I can put a peak that includes your entire desk, and I'm going to have a 100% chance, right? But if I start dividing your desk up into parts, I'm going to have the middle, which is the highest chance, right? And so I got the most intensity there, don't I? Okay, the most probability, which would be the same thing as an integration or area in this case. And then if I look at the left part of your desk, well, sometimes you all are leaning over on your desk, aren't you? And so I'd have some amount of that concentration of your presence at that point one time. And then sometimes you're leaning on the other side of your desk, aren't you? And so I'm going to have some of your population there. Okay? Same thing's going to happen here. Right now we have nice, clean individual peaks that look very easy. The area is fairly easy to kind of guesstimate from just the height, right? But if you start dividing this out in smaller peaks that are right on top of it, that's going to get more difficult to guess from the heights, right? So remember, it's not actually height that tells you the probability, the amount. It is the area, right? This right here is an integration trace, and it literally just goes from here at 0, and then it does the area under this curve, and that's the amount right here. Okay. Now this area under that curve, that's going to be directly proportional to the number of hydrogens that are causing that. Okay. And so when you look at this right here, if you were to do these ratios, you would see this is like 1 here, right? And this is like 1.5 versus that 1. Okay. So if you were to look at this one's about 50% larger, isn't it? See that? Okay. Now, whenever you do these areas, you're actually best off just taking those numbers and getting at least the whole number ratios for those, okay? Because can you have a 0.5 hydrogen? No. It's a ratio, isn't it? So we're looking at the ratio there, okay? And so in this case, this would actually be 4 hydrogens right here, and this one would actually be 6. This is 1.5 times the number of hydrogens, right? It's 50% more hydrogens, okay? Yes, if you're typically going to have to do an integration for most of these things, and it's not a very simple case of where the heights basically match up, most of these graphs, the integration line's included, period. Okay. Some of the older ones, the integration line's not included because it's an older spectra, but typically they don't have the resolution that it matters. So you can just measure the heights versus each other and you'll get basically a good approximation. Okay. Remember, whenever you do the number of hydrogens versus each other, if you were to get, let's say, I was to do these numbers, I'm measuring these out, I'm trying to figure this out, and I got, okay, I think there is 6 hydrogens here, and I think there's 3.9 hydrogens here. What would that actually be? Yeah, 4. Yeah, you can't have a 0.9 hydrogen, right? So keep that in mind that you, if you're very close to a number, you probably just need to round. Okay? You can have a little bit of error whenever you're measuring things out. Okay. Okay, so let's talk about splitting, all right? So splitting is literally where these peaks are going to split. Okay? And what's happening is that you're going to get a just small, tiny amount of change in that chemical environment. Okay? And it's not going to be enough that it's significant changes in these chemical shifts. It's just going to be barely enough to be able to be detected. Okay? So this is what they look like if you just have the same spectra as we were looking before. You do need a high enough resolution instrument. If it's not high enough resolution, they would just be like this. And you wouldn't see any splitting within that. Okay? So it does need to be high enough resolution that you can actually see these like 0.1 differences. Okay? Now, this right here is the splitting. So we're zooming in here so we can see this. This is high enough resolution instrument. We can see very nicely, actually. And so you're seeing that splitting. This one is this hydrogen right here. Okay? And this one right here is these 2 hydrogens. Don't mix this up that the number splitting has anything to do with the number of hydrogens that it is. Okay? I'll get into it. I just don't want you to, yeah. It's very common for people to like dart forward there and then have a hard time getting that out of their head. Now, every proton, if you remember, is going to be a little bar magnet, right? And so what we normally have here is we have this spin state. We have an alpha spin state and a beta spin state, right? So 2 different spin states that can exist. Okay. Okay, so if you have these little magnets next to each other, right? Has anybody played that Magnetic Chess? That's that new game that came out recently? No? Nobody? That's a little sad. If you get a chance, it's like a couple bucks. You can get them at stores. You put like a circle with a rope, and they give you these uneven magnetic pieces. They're very like lopsided, and so every magnetic piece has a very weird way it rests. Okay? And then you place them down, and whenever somebody causes the magnets to collapse together, they have to take those magnets back. And so the first person that runs out wins. Okay? And so it's kind of cool because it actually shows you magnetic field alignments, and they all end up in crystal fields. So, hey, I really need to, if I teach general chemistry again, I really need to, when we get into crystal fields, have everybody play that game. Because they always end up optimizing to crystal fields depending on their shapes. Because that's what a crystal field is as well. So it's literally a magnetic field arrays that you're playing with. Yeah. So it's the same sort of thing you're experiencing with these. Whenever you have these magnets, right, you're moving around in space. If you put another magnet nearby, what's going to happen? They're going to interfere with each other a little bit, right? And so depending on the states you have, you're going to have a different interference, aren't you? If the north poles are facing towards each other, you're going to be trying to flip, aren't you? If you have a north and south, you're going to be trying to pull together, aren't you? And so you're going to change that magnetic field just a little bit. Barely enough to be detectable. Okay? Okay. And so what this is referred to is, remember what we have those spin states? Well, this is referred to as spin coupling then. Okay? And so they're going to interact with each other through this spin-spin coupling. And whenever we're talking about the protons that are doing this, we call them coupled. So they're going to be coupled to each other. Okay? And so these protons right here, these two versus this one, these hydrogens, these protons, they're experiencing coupling. And that's what's causing this effect here. Now, what we're going to end up with is we're going to end up with an N+1 rule. And I want you to keep that formula in the back of your head as we just talk about what exactly this gives us. Bless you. Okay, you may already be able to deduce this. Notice this hydrogen's experiencing 3 peaks right here, right? It's split into 3. This one, these two here, are experiencing 2. So if you pay attention, there's only one hydrogen around these two. So the hydrogens that are around those set is 1, right? 1 plus 1 is 2. This one right here is experiencing 2 hydrogens next to it, isn't it? And so 2 plus 1 is 3. And so what the N plus rule is, it's always the hydrogens that are next to it. Okay? So a set of hydrogens experiences the hydrogens nearby on the next carbon over. Okay. So if we have a proton A, it's going to be coupled only to proton B, and there are inequivalent protons B. Then we're going to have a proton A that has N-coupled protons. That's that N number of protons coupled. Now, the signal for proton A will then be split into N+1. And so we'll get that N number of coupled protons plus 1 extra peak. Okay. So this is how that breaks down. Again, this is just the number of coupled protons, the number of protons that are next to it. And then right here is the N+1. Now, this is what this is called. Sometimes they do actually put these letters for what the coupling is. It is like if you were to look at a table of these assignments, you guys kind of remember how they had tables of the common fundamental groups when we were looking at the functional groups for infrared. They had like a table, weak, strong, medium. Yeah. This is oftentimes how they do that. So they would put singlet S, doublet D, triplet T, quartet Q, and then quintet is QN. And then after that, they put multiplet, and they don't really specify. They may put a number to specify if they can figure it out. But sometimes it gets so much that it overwhelms the resolution of the instrument. Or it gets so complex that it's just not worth really talking about. Because it doesn't really provide you that much information then. Okay? This would be the relative peak hikes that you would see. And so when you looked at that doublet, you may have noticed that it's about the same for the peak heights right there. When you look at the triplet, on the other hand, which is right here, notice that when you're talking about these areas under these curves, it's about a 1 to 2 to 1. Okay, remember, it's the area under the curve that actually bounces. Okay. And this is how this would break up on the rest. This would be a quartet. You would see the outermost ones would be a intensity 1 or a integral 1. And then the inner ones would be a 3 times that. Okay? And then you would look at the quintets, and it would be a 1, 4, 6. Okay. Okay, so again, that N number, if I have 3 protons, I have the exact same chemical signature, they're in the same place. Is that going to do anything to the splitting? No. That's nothing at all, right? It's the ones that are always nearby, okay? It's the ones on the next carbon over. Okay, so equivalent protons, these do not exhibit splitting. So if you have ones in the same equivalent set, they're not going to cause splitting, okay? And so this is a case where you got to be careful that you can't just go next carbon over and assume, bam, it's going to cause splitting. because these are chemically equivalent right here, right? That's one set of chemically equivalent protons right there. Okay? And because they're at these same energies, they're not going to cause splitting. Okay? They're not going to couple. And so these will not couple with each other. Right? This is actually why, even though this is taken on a fairly new instrument right here, you don't really see any splitting. Because you have one set right here, and then a blank carbon with no hydrogens, and then your next set is over there, right? And so none of these are close enough to couple to each other. You don't have another set that can couple with each other, okay? This is actually one of the reasons why this example is given before and after, because it's a great example of what to look out for not doing this, so that we can compare it to what example that does do this, right? Which was the next one over here. See that? Okay. And so you have the example of like hydrogens, common issues students would get that they go, oh, I think that would cause coupling. This is the one that doesn't, okay? So chemically equivalent don't cause splitting, okay? They don't couple. All right, so let's look at an unknown compound. It produces an HNMR that has just two signals, each of which is a singlet. Which of these compounds could be the unknown? So what are we looking at? What two things do we want to concentrate on here? Chemically equivalent protons, right? And then we want to think about, well, if it only has a singlet, right? It can't have two different chemically equivalent protons near each other, can it? Only two different types of hydrogen atoms, and they can't be next to each other. So somehow you gotta keep them apart. Okay. Everybody have your answer in mind? I'll give you another minute. See you can. You're probably like, what in the hell did I walk in on? Oh my goodness. Or maybe you all are sitting here and going, what the hell did I walk in on today? Admittedly, is a little bit of a dense material for your first day back. But that's how the cards fell. Okay. Got your commitment? Okay. Okay. All right. Everybody make sure you commit to your answer. All right. So, how many chemically distinct protons are indicated in this spectra? Two signals. So how many distinct protons? Two. Yeah. Has to be two, right? And these two distinct protons, so these two sets of protons, they have to, can they be near each other? No. If they're near each other, that would cause splitting, wouldn't it? And the fact that we have singlets tells us we shouldn't have any splitting, right? And so there's several ways you could actually go about this, but the easiest way to make sure that you got the right answer is if you were to just sit there and go, how many peaks should I get out and how many splitting should I get out? Okay. So this right here has two sets. Cool. That's that A and B, right? But they're on the adjacent carbons to each other, and that means they should exhibit splitting, shouldn't they? And so this set right here would have one adjacent set, and that would give an n of 1, and then n plus 1 would be 2. And so this right here, this set, would also have then one adjacent set, because it's next to A now. And that would mean we have an n of 1 for each of these. And so we're going to have a splitting that is considerably greater than 1, right? Did I put the splitting for the numbers? Might have. Yeah, I'll have to double check. Okay, so when we're looking here, where these ones here that the sets are next to each other, they can't be. So 1 and 2 can't be. They're going to have splitting. They can't have singlets. These here, this has 2 sets. This one's a little hard to see that has 2 sets. It has the E and E, that's the same environment. Everybody see that? That's symmetric. And then F and F are the next. And these are not next to each other, so they won't cause any splitting. And they're not next to each other because that has 4 bonds on it, isn't it? So these 2 sets of protons are not next to each other, so they're not going to cause any splitting. This right here is actually just 1 set. So every single hydrogen in this number 4, that would only give you 1 peak, right? Okay. And it'd be 1 peak with no splitting. Okay, so the only option would be 3. Did everybody get that okay? Okay. All right, so let's look at this origin of the n+1 rule. Now again, if you think about these B locals, remember that you're going to have the external field that's applied to this, right? And that external field is always modified by a local field, okay? And so whenever we look at these external fields modified by a local field, if you have 2 different magnetic fields next to each other, they're going to modify the B local, aren't they? They're going to change that B local's strength. And because they're changing that B local strength, then what you're going to get is a very, very tiny shift, right? And so if you only have the 1 proton next to it, okay, so these are 2 chemically distinct protons. I know that we haven't specified anything else there. Just imagine there's, whatever groups that make it chemically distinct. And so you have this hydrogen right here that's being detected, and that's that peak right there, right? And then you have this other hydrogen, and it can be in 2 states, can it? It can be the alpha or beta in terms of its spin, okay, or up and down. And so if it's in the up state, then it's going to modify that peak in one direction, isn't it? If it's in the down state, it's going to modify it in the other direction. And that's what you're seeing right here. Yeah. And, they're about equal because the populations are about equal, but they're not quite equal, are they? Because we've actually caused more of them to be in one spin state, but not a huge amount. We don't cause a huge difference. We just cause a small difference. And that's why you see they're about equal. They're never truly, completely equal, but close. Okay, so what if we have 2 hydrogens over there? Okay. So now we can actually have 3 different ways that these can line up for spin states, can't we? So each of these hydrogens can be in an up or a down spin state, right? I'm going to use the arrows up and down. Is everybody okay with that? Up and down spin state? Corresponding to alpha beta spin states and plus 1/2, negative 1/2. Okay, so if we get both of them up, okay, then both of them are going to align and cause that magnetic field to shift in one direction. And so you'll get a increase, okay? If both of them are down, then they're both going to do the exact same thing, and they're going to give you that other split right here, okay? And so these are going to give you the 2 splits on the sides, which are they're both up, or they're both down. And remember, this is like a coin flip, most of the time, okay? If you're doing nothing else, it'll be a coin flip. It'll be 50-50 chance of being up or down, okay? Heads or tails. Right. Now, what happens if they're opposite spin states? Well, they're going to shift it in both directions at the same time, aren't they? They're going to do it equally. Okay? And so if you get the opposite spin states where one's up, one's down, then what you're going to see is that you'll have no overall shift. Because one would have shifted it up, one would have shifted it down, they're just going to cancel out. Okay? Now, if you were to do this with a coin, right? What's your chance of hitting 2 heads? Anybody know how to do that? 25%. And that's because it would be 1/2 times 1/2, right? Yeah. And so 2 heads, 2 tails, those both have the same chance of happening, which is 1 in 4, right? What about 1 heads, 1 tail? It's going to be, well, for each of these, it would be the same thing. But if you don't care about the order, then you end up having it be 50% of those, isn't it? Huh? Because it can happen in 2 different orders. You could go heads, then tails, or you could go tails, then heads. Or another way of saying that is you're actually the 1-to-1 ratio, aren't you? Yeah, they're going to be in the same group, so you're going to get 50%. Mm-hmm. This is why this is double the height. Exactly. Is because you have double the chance of that happening. And so your population that's in this state here is going to be twice the population that's in the other states. And so that's what gives you that stronger peak right there, that higher intensity, the larger area under the curve. Now, these are actually the reasons for all of these ratios that we talked about in this table here. Okay? So if you sit down and generate these, which we're going to do for a few of these, we're not going to do it for every possible one though, then you're going to see that, again, this is just the ratio of probabilities for a 50-50% split, right? So as you get further out, you get smaller. You'll notice it's kind of a quasi-Gaussian because we don't have a high sample size. So you can't get perfect Gaussians. It's pretty close. All right. So this right here, again, is going to be the where you have 3 different hydrogens here. And so now this hydrogen here is being affected by 3 ones here, right? And so we would go in, that's 3 here, that's the number. And then plus 1 would give us 4, quartet, right? And this is why. Is because you're going to get 1 peak from all 3 of these being the same thing, right? And then you're going to get another peak for 2 being the same thing, and then 1 being the other, right? And so this is up, 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 down, and then all the combinations there. Just 3 times more likely than being all ups. And then you get up, down, down, and that's all the combinations there. And then you get all downs, don't you? And that's the split right there. Okay? That's just what you're seeing every time. So it's not as scary as you may have thought and your first impression would have been, but it is a lot when you look at the entire spectrum. It can be quite a bit. This is actually how you would figure this out fairly easily. It's called Pascal's triangle, and it actually does the math for you very, very easily. Okay? And so what you'd write is you just write these as descending order in a triangular shape. Okay? And so you start with 1. And so 1 plus nothing is 1. And so your next row is going to be 1, 1. Okay? And then you come over here. This is nothing, 0 here. So 0 plus 1 is 1. Down here between these two, 1 plus 1 is 2. And over here you have 1 plus 0. And that gives you 1 again. Okay? And you just come down like that. So 1 plus 0 again, 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 0 is 1. Okay? And you can generate any amount of splitting that way if you just keep going. Okay? And that will show you the probabilities of those. By the way, it works for probabilities too. If you ever want to figure out like what's the probability of me getting this specific combination of heads, tails, it works for all those. Okay. It's actually a very useful graphical tool for math. Okay. Right. Everybody okay with that? Okay. Now, this only works because of one key factor, right? Our alpha beta spin states are approximately equal. Okay. If they are not approximately equal, then this would not actually give you this math. Okay. And so they're approximately equal, they're not perfectly equal, right? And so you're going to get very, very, very close to that math. Actually, it predicts quite well. Okay. Now, whenever we're talking about these, the reason these spin couplings are happening is because they're in relatively near each other in terms of energy. Okay? If we start looking at something like an OH or an NH, the OH and NHs are not going to give you spin coupling. Okay? Because they're going to be significantly different from each other. Right? Or another way of thinking about it is they are so far apart in terms of energy that they just don't couple. Okay? So what we can actually see that right here is we have this CH2 here, right? Okay, you may be tempted to think, okay, well, you should think hopefully that, hey, I have CH3, right? And so I have 3 hydrogens on the next carbon over from this that are chemically distinct from it. Okay. And so my N number would be 3, right? And then plus 1 is going to be 4. Okay. And so I should have a quartet. If you look over here, you're going to be tempted to think, hey, I have another 2 hydrogens. I can't actually hear you, but... So this is one set right here. Yeah, and this is another set. And these are another set. Yeah. So you have 3 distinct hydrogens. But these one, because they're on an odd nitrogen in this case, they don't couple with the carbons. And so what you see is the splitting doesn't happen for these from those hydrogens. Yeah. They only happen from the CH3 right here. And then, of course, the CH3 just has these ones because it's at the end. So, okay. So remember that you have the OH and NH. They're going to not tend to exhibit coupling. This is actually because, see how broad this peak is right here? Can everybody see that? It's super broad. And so it looks very shallow right there. This is the nitrogen hydrogen peaks right here. And the reason it looks like this giant smear is because when you look at an OH or NH, those are way more acidic. And so they actually rapidly are going to do proton exchanges and move on and off. So they're literally like coming partially off, coming back on, and they're doing that pretty rapidly. Things like the exact same reason you get hydrogen bonding. Yeah. Yeah, and that's only a factor when you're talking about oxygens and nitrogens. You'll typically notice pretty easily because they're very broad peaks. And that's the same reason you're getting the very broad peak, is you're actually seeing this hydrogen in a bunch of different, very slightly different states. And so you get this big smear here. Okay? And that's actually the same reason that you see the infrared too, by the way. That the OH on the infrared is very broad and smeared, is because you have it in a bunch of different little states. In that case, most often hydrogen bond is the direct contributor there. Now, interesting side note to this is there is fast response NMRs, just like there's fast response MRIs. And so if you're fast enough with your spectra, you could actually see individual peaks here for the different states of the hydrogens. Normally, though, these proton transfer reactions that are happening in here are just so fast that you won't be able to see anything. Okay. Oh, the other thing to remember is these hydrogens are coming partially off and on all the time. If you put this in with something that has deuterium that can come off from it, which is pretty normal for the solvent for this, it can get replaced. And so that's one of the reasons the intensity is so small here, despite the fact that it's two hydrogens, is because oftentimes you're going to put this in a deuterated solvent. And so because these are coming off and on very quickly, they can actually exchange with the deuterium. And so you can end up with deuterium here, rather than having the hydrogens like you meant to have. And so you can actually get, you normally will see these far, far, far smaller in intensity than they should be. Okay. Okay, let's talk a bit about some coupling constants and more complex signal splitting. And so these coupling constants, depending on how far away from each other they are and what they're coupling across, are going to be tend to be different. And so by measuring that distance between the coupling, that splitting that happens, you can actually tell what the relationship is. Okay? And so again, we're working down that priority of ease and importance, right? So don't forget, whenever you're doing these spectra, you always want to start at the easiest to deal with, which is always the most important stuff we talk about, right? Which is always the beginning, right? And then you want to work yourself to more complex uses of these, because complexity means room for error, right? So the more complex something is that you try to perform, the more likely you are to screw up. So you always want to work from simplicity to complexity, right? Okay, so these right here are actually the coupling constants. You'll notice that they're going to be J. They'll be measured in hertz. You'll note that these are actually much, much smaller numbers than we would normally be seeing for our other stuff, okay? These are really tiny in energy compared to what we're looking at for entire chemical shifts that we were talking about before. So small that you have to zoom in to even see them, okay? And so typically your spectras are going to look like this, right? You're going to have like the overall spectra, and let's be real, could you measure that at all? No, it's way too small. And so you'd have to zoom in and actually measure these when you're zoomed in, okay? They are going to be peak-to-peak measurements. And so when you're talking about the carbons, just carbons next to each other in an alkane, they're going to typically be somewhere in the 6 to 9 hertz difference for these couplings in terms of energy. When we're talking about the next one over, they're going to be incredibly small. In a normal instrument, you would not be able to detect these or read these. Okay? Now, having said that, science is evolving, and there are instruments that can indeed measure the next one over. Okay? But you'll notice that compared to whole numbers right here, these would be fractions of a fraction. They're going to be incredibly small, because remember, magnetic fields are a cube root. They go down tremendously very quickly, right? As you go further away. Okay, this is across a nice carbon double bond, and what you'll notice is that it's going to actually amplify this coupling. Okay? And so we'll actually have numbers in the 7 to 12. It's not like completely different, but it is, higher. This would actually be on the opposite sides of that double bond. And what you'll notice is being on the opposite sides of the double bond, again, is going to significantly amplify this coupling constant. So this one's actually in a completely different range, isn't it? And so very distinctly different than the others. This is where it's the geminal, where they're on the same side of the double bond. And interestingly enough, because it's on the same side, it actually dampens that effect. Because remember, you have that circuit above and below when you're talking about these double bonds. Yeah. So this is actually going to dampen the effect here. So if you had these geminal hydrogens and they were chemically distinct different, then you're going to experience a splitting, but it's going to be pretty small. It's going to be a 1 to 3. This right here is going to be on a carbonyl here. That's that carbonyl hydrogen, like an aldehyde. And again, because of that circuit above and below, because of the double bond, you get, again, a very tiny effect. Yeah. Okay. Interestingly enough, if you look at the hydrogens across a benzene ring, you can actually get these on like fairly moderate instruments. Modern day, what we consider fairly moderate instrument. There's still like a $50,000 instrument at least. Still, for NMRs, that's pretty moderate. And so that's the relationship here. These are because that benzene ring, remember, has the amplification effect. Okay. And so right here we have some more coupling constants we're looking at. So if you have these coupled protons here, what you're going to see is that the coupled protons are going to have shared coupling constants because remember, they're coupled, and so it's that coupling of their spins that's causing this. Okay? So what one experiences, the other experiences from it. And over here we have another, we don't have to worry about these mixing with each other, by the way, because we have the extra carbon there, splitting it apart. And right here we have the CD set. And again, you can see here that has a 7.6, 7.6 coupling again. And so we're getting that same split. Okay. That's another thing that can actually be used. There's some really cool work that's been done. It's called 2D and 3D NMR. And they actually take all of this information. You need to use a computer usually to do it for anything that's larger than like 10 atoms. But when you feed that into a computer that's been properly programmed and has the proper work on it, it can actually then resolve what like entire enzyme structures are. And so you can do some really cool stuff with that. Well, let's see, did I do it? Okay. Now, one of the things I want to point out is this I actually have listed a couple cases of what are called long-range coupling. Okay? And that's going to be where instead of being on the carbons that are next to each other, they're on the next carbons over, right? So this is a case of long-range coupling. And they typically only happen on something that's highly conjugated. Things like a aromatic ring. Okay? And so for this aromatic ring right here, if you have something that actually has some sort of chemical splitting for this, like a methyl substituted on these things, you can get more coupling than you might think. Right? They're going to be very small coupling, so they're going to be really close to each other. Okay. Now, we haven't seen something that close to each other yet on these. And so we're going to see that a little bit here. See how close these ones are to each other? That's what it looks like when you're coupled and you're only like a 1 hertz, a 3 hertz, that sort of thing. These are those geminal ones. See that? And so when you're experiencing the coupling from the geminal ones, the ones that are on the same carbon right here for that double bond, that's like a 1 to 3, right? See, even zoomed in, what happens here? Right there and there. You get this very tiny amount of coupling, okay? Now, this is going to be your first example of what's called complex splitting, right? It's going to be coupling something that's coupled. You've noticed before we've avoided this. See how every time we've done this before, we only had 2 chemically distinct sets, right? And then we purposefully left a carbon with no hydrogens on it in between so we could avoid the issue. Okay. So if you've been wondering why every single one of these compounds had a carbon with 4 bonds on it, that's why. We've been avoiding complex splitting, where we're going to have a coupling that then couples. Okay. Now, what you're going to see is that couplings that couple, or complex splittings, is literally just going to be the coupled set that then splits that set into a new coupling. Okay? Okay, so let's go ahead and look at a splitting diagram. Diagrams are going to be the easiest way to understand this. So right here we have the one peak, nothing's coupling with it. This is what that would look like, right? And so if we just had one chemically distinct hydrogen set, that's what that would look like. Okay. Now, we have here hydrogen B that we're going to be considering. That's that one there. Everybody have that one in your head now? Okay. Okay. Now, hydrogen C here has the largest coupling, right? And so this is going to give you the largest contribution for coupling. This is going to be 7.1 hertz, and that's what that's going to look like. Okay. And then what we're going to get is hydrogen A, which is that geminal one, and that's going to have that much smaller amount of coupling. In this case, it's going to be 1.6. And so what we get is the first one couples, and this gives us the doublet. You see that okay? Okay. And then we get that coupled set, now it's going to couple with the next one. And so we're going to couple that with HA. And that's going to split these peaks by that coupling constant. And so what we get is we get a doublet of doublets. Okay? Now, that's not quaternary, right? It's going to be a different thing than a quartet. Okay? It's going to be very distinctly a doublet of doublets, right? So we split a split. Okay. So this one's going to actually be looking at the HB if we were to have it the other way around in terms of splitting. And so if we were to look at this the other way around in terms of what's going to cause the splitting first, this is what that would look like, okay? And again, it would generate a doublet of doublets, but it would look distinct, wouldn't it? So if we split it by the HA first, this is what that looks like. And then if we split it by the larger 7.1 hertz split, notice that they're going to actually interlock like that, aren't they? Okay. And so it doesn't look quite as nice. However, what do you notice about this actual pattern down here? Do those actually look different? The numbers are different up here because we have the numbers going from here to here. But if you were to just look at the peaks and overlay them and ignore the red and blue, they end up the same, don't they? Yeah. Yeah. So you still get the same pattern at the end. Okay. Now, this right here is going to be a triplet of doublets. I know. So fun. Now, so we have the 2 protons here. These are going to be split. This proton is going to split the two protons into a doublet then, right here. And so we get this triplet is being caused by this. So this is the hydrogens we're splitting. This causes a triplet, right? And this is then going to cause a doublet. And so what we end up getting is a triplet of doublets. And so see the 3 sets of doublets? Okay. All right. Notice the height ratios are going to maintain the same as if you were to do each of these separately. They're just going to still maintain the exact same height ratios. So you have that 1 to 2 to 1 here. And then you end up with 1, 1, 2, 2, 1, 1. You just get the exact same splitting. Okay, so let's look at the signal resolution and strength of the B local. So you see here that we get CH3s, and because we have these CH3s so close together, what we end up seeing is that it's kind of a jumbled mess. And in fact, can you see how these peaks right here, some of them are like lopsided? Like this one here. Yeah, it's wiggly, isn't it? It's like it's lopsided. And that's because it's not one peak. Okay. It actually has multiple peaks under there, most likely two. Now, this is actually using a 90 megahertz instrument and a 300 megahertz spectrometer. So the next one is going to be the 300 megahertz spectrometer, but I want you to have this one in your head. Everybody ready to see when we use a 300 megahertz spectrometer? Okay. That's what that looks like. It helped a lot, didn't it? It was two sets of triplets, wasn't it? Okay. And what's happening there is the same thing that would happen if you use a low resolution camera, right? Is like it looks like parts of sticks and fences and stuff, or one big blur, and you kind of pick out a little part of the fence here. And then you use a higher resolution camera, and what do you get? You can now separate the different parts of it, can't you? Okay. And so this one's the 300 megahertz instrument, by the way. That one's the 90. Okay. And so the more powerful that magnet, the better you can resolve, and the spectrometer is going to become more powerful alongside that magnet. So the larger the external magnetic field you apply, then the larger that you can get in terms of frequency differences, can't you? Okay. And you don't really notice that frequencies or differences are getting larger because this is all chemical shifts, right? It's a relative scale. Okay. Keep that in mind that that's actually the reason that chemical shifts are used, is so that you can compare different instruments, right? Okay. But when you use a more powerful magnet, your frequencies for these splits are going to increase. Okay. And so you're going to get larger frequency differences between these different peaks. And so you can shift things that are very close together further apart. So you can more easily differentiate them. Right? It works a little different than, I know I like using camera examples because you all have cameras and use it. But it's more like instead of getting a high resolution camera, you just took the entire world and went and split everything up more so it could resolve better. That's actually what's happening here. Okay? You're literally just changing the entire world of the proton, right? Now, one of the things we need to talk about here is that the coupling constants are actually independent of the B external. So regardless of the strength of the B external, you're actually going to get frequency differences between the peaks. These splits, those are going to remain unchanged, actually. Okay? And so that's why these resolve so nicely now, is it's the peaks that resolve and get further apart, not the splitting. Okay? And so before, these were overlapped with their splitting, and so you got a big mess, right? And then we basically took the entire world for the proton, applied a more powerful magnetic field, and split those up. And now we can see the splitting for each one. Am I over time? No. Okay. Thank you. Okay. So remember, if you guys remember the math we talked about before, larger external magnetic field was going to cause a larger delta E spin. And so that delta E energy difference for flipping those proton spins, right, is going to be larger the larger the magnetic field. Okay, and that's what's being measured in terms of 300 megahertz. 90 megahertz means you have a 90 megahertz delta E spin, right? 300 megahertz would correspond to a 300 megahertz delta E spin. Okay. All right, now this right here is actually what those peaks look like. So again, here we have our splittings. And then what we're doing is we're actually taking this entire set of peaks and we're moving them further apart. And that's what you're seeing here. So this is the 90 megahertz right here. This is actually what you're seeing in terms of these peaks for this one right here. And then this one over here is like that 300 here. And so we're moving the center portions apart. And that's going to cause you to resolve all the other. Now, notice that because we're using these chemical shifts instead of using like hertz and frequencies here for these numbers down here, that it causes a bit of a weird looking spectra change. So what you end up getting is you get, yeah, it looks basically the same for these numbers here, right? And it actually looks narrower now, doesn't it? It looks like we fine-tuned microscope or something. It's a little blurrier here, but they're same distances. Yeah, it looks not like you would think, does it? Okay, but remember that's because these are all chemical shifts. They're the they're the frequency over a frequency, right? And so these numbers here between for the splitting not changing, are they? These numbers, however, are getting larger and larger and larger. Okay? And so that's going to cause your spectra to look like the bands are getting more narrow. Okay? You'll still be able to resolve them very well. You'll actually be able to resolve them just well or better. Okay. So let's look at some carbon signals here. So this is going to be C13, nuclear magnetic resonance spectroscopy. Again, NMR, but instead of using hydrogens, we're going to use carbon 13s. Okay. Now, carbon 12 has a bit of a problem for us, doesn't it? Yeah. Carbon 12 is not an odd number. Yeah. So we can't detect carbon 12, which is the vast majority of carbon. And that causes an issue here. Okay. Above and beyond the fact that we're trying to do this for carbon. Right. So when we're talking about a carbon 13, that's like 1.6% of all the carbons in a sample, isn't it? Yeah. So by definition, we're automatically losing the vast majority of our sample, aren't we? Okay. Now, the other thing that's happening here, that carbon 13, again, has that same two available spin states. We have an up and down. They're differentiated because it's odd. So it's uneven in its spin state. Spins, it has one side that's a little uneven from the other, right? And so we can differentiate those. Now, when we're looking at these, the RF radiation we have to use for these, this is going to be very different, significantly different than we use for hydrogens, because something that weighs 13 is not going to spin the same as something that weighs 1, right? And it's not going to require the same amount of energy to flip, is it? It's like if you tried to flip your desk, you do it really easy, right? If you try to flip the building, it's going to take a lot more work, isn't it? Okay. And so that's what the gyromagnetic ratio is. The gyromagnetic ratio of carbon 13 nucleus is actually going to be about 1/4 of that of a proton. So if we were to look at these spectra, even if we were running an HNMR, what we would see is that we would never see the carbon ones because they would appear outside of our window. They'd appear way, 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 way up. And then they'd be very, 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 very tiny. Okay? And again, remember that one of your biggest challenges is just the sheer low abundance of carbon 13 in this. Okay? Notice how this doesn't look very nice, does it? See that? Looks bad. This would be a similarly powerful signal instrument as what we've been seeing for the HNMRs. And what you're seeing is noise, okay? Because we have such a small population, just the ambient radio frequencies coming through is all of this stuff down here. And that's called noise. All right? Now, what we can do is we can take a bunch more signals, we can take a bunch more spectra, and then we can average them together. And because the noise is random, it's going to average down to 0. And so we get this right here. Okay. It would be like, you guys ever seen like old filmography? They set up like the film. It wasn't very good at capturing light. So they left it there for like 15 minutes and just exposed for the entire 15 minutes. Get those old photos. Similar. Very, very, very similar. And you got like this grayish background, right? Because you're getting ambient light that was kind of randomly doing it. But then you got real dark, distinct lines where the person was, right? Yeah. That's what you're saying. One of the things that I should point out while we're doing this is you may have already kind of figured this out, but if you only have like 1% of all your carbon in a sample being C13, what's the likelihood you're going to get two of those next to each other? Very low, right? Like 1 in 10,000 sort of likelihoods. So we're talking about like, at best, like 1 in 1,000 sort of stuff, right? So when it comes down to splitting, essentially that's going to be almost unheard of. Now, oftentimes when you do these, one of the things you got to keep in mind is that when you do the carbon spectra, there's not a lot of organic solvents that work. They don't have carbon, right? And so we can't really do the deuterated, and it's already such a small amount that's very difficult to isolate the C13 from the C12. And so what you're going to typically see is you're going to have to put a solvent in there that's just very chemically shifted so you can try to get it out of your way. Okay? And so that's what you're seeing right here is we've essentially just put in a solvent. It has 3 chlorines on it, right? And so we put in something that's just shifted really, really far over so that we can try to get it out of the way as much as possible. Okay? You can't really do what you did before where you just D. Change out all your hydrogens to D, right? It's not really going to work. Technically, you can do it. It's just so expensive that nobody would actually be able to afford it. Yeah, it'd be millions of dollars per sample sort of stuff. And then you have to do it in solvent ratio amounts, which is not happening. So, again, the signal splitting is essentially going to be unheard of. It's going to be incredibly rare to the point where you probably would never see it. Even if you did CNMR all the time every day, the likelihood of actually seeing it in a large enough intensity that you can actually do anything with that is very, very unlikely. However, under conditions where the spectra are acquired, we typically don't observe the signal splitting. Again, it's going to be like and you have 1 in 100 peaks, and you're going to have like 1 in 10,000 intensity for the C13s. Now, the protons, so when we're talking about the splitting of a carbon signal, these protons are actually going to cause some degree of splitting because they're surrounding those nuclei, right? So we have the carbon in the middle, right? And then we have the protons coming off in the form of the hydrogens, okay? And those hydrogens, they're going to be, active in this. They're going to be H1s mostly, aren't they? And so what we are going to get is we are actually going to get those attached protons. They do cause splitting, but we don't see them in the spectra because they're going to be broadband decoupling that we use. So what we're going to do is we're going to use broadband decoupling to essentially turn off the coupling between the C13s and the H1s. Because if we allow those to couple, what we end up with is a very split, and then we already take something that's very low intensity, and we split it up among multiple peaks, right? And so that causes even more problems. So typically what you're going to see is we're going to decouple those as best we can. And that's called broadband decoupling. I'm still okay for time. There is a type of spectroscopy where we're going to take that information and actually try to use that. That's going to be called DEPT spectroscopy. And that's going to be using that coupling with the hydrogens. Okay. And yeah, if you're like, well, Dr. Clausen, you're losing information that you could have otherwise gotten. You are exactly right. We are losing information, but it usually is worth it so that you don't have to try to read something like that, right? With a bunch of peaks everywhere. Yeah. Okay. So this is going to be a C13 NMRs. This is going to be what their chemical shifts look like. So for example, right here, that's your TMS. And again, that's going to be set to be 0. Okay. We can still use that because it has carbons on it. So right here, this is going to be a normal CH3, and you're going to see that show up somewhere between 10 and 25 for your chemical shift. Here's a normal CH2. So again, that would be in the middle part of the chain, right? And that's going to be 20 to 45. You'll see there's a little bit of overlapping here, and these tend to have broader regions they can be in. Okay, so this one right here is with the 3 carbons on it, and that's going to be 25 to 45. They're pretty overlapped again. And then here we have 30 to 35. Now, this is going to be off of a BR here. And see, when you have something that's fairly electronegative, it's going to shift it a bit. The more electronegative you have, the more it's going to shift it up. And there's the chlorine, more electronegative, shifting it further up. Okay. Now, generally speaking, the HNMRs are going to happen between the ranges of 0 and 12 ppm. And then we were talking about the CNMRs, they're going to happen in the range of like 0 to 220. Okay. And so you're going to have much larger shifts for the CNMRs typically. Now, the tables in these for these two things are typically lined up in such a way that the tables will read almost the same orders. And so you'll see like same functional groups near each other. Okay. So that you can find them a little easier. Right here, for example, we have our double bond, and that's where we start getting these huge shifts, right? And notice like a benzene ring, massive shift, right? Okay. Okay. And there we have those. Now, much of the same thing that's going to happen with the HNMRs is going to happen with CNMRs for chemical shifts. And so what you'll see is that they have a very similar trend. They are extremely analogous. The sigma bonding electrons do shield the carbon nucleus. The greater electron density will contribute to this. If you have something that's electronegative, it can de-shield it more. And if you have something that's like a conjugated system or you have a pi bond, that's going to cause that same circuitry that we saw before with the H. Okay, I guess we will start up here next time. You all have a wonderful day after break. Hopefully everything goes well and smooth as you reintegrate into your schooling. Dun, dun, dun.
Yeah. I literally missed it as soon as I walked in.
You
Saw it
did.
vanish.
Yeah.
Yep. Thank you. Good day.
You have a wonderful day. Be 6.